Okay, so welcome to this session about the acids and bases, and specific some questions about the weak acids and how to solve the related questions. To start with, let's just revise the main formulas that we have been studying so far. So basically, we learned so far that the pH, which is P here, it belongs to the minus log. pH equals to the concentration of the hydrogen ion. So if you are given the concentration of the hydrogen ion in the question, or if you are able to get it, then basically you can calculate pH. Also, if you are dealing with a basic solution, so instead of pH, you will be dealing with the OH, and BOH will equal to minus log the OH. Now, in some questions, basically, you will be given the pH, and you'll be asked to find the concentration of the hydrogen ion. So all you need to do is the anti-operation of the minus logs, which is the 10 to the power of minus pH. So the value of pH here, you raise it to the minus of that 10, and then you'll be getting the concentration of hydrogen. And same applies to the OH. We'll take some examples as we go along. Another important formula that we learned, which is concentration of hydrogen times concentration of OH equals to 10 to the power of minus 14. And if you were to take the log for the whole equation, or minus log, basically it will give you pH equals plus BOH equals to 14. So far we have learned 1, 2, 3, 4. So these are the equations we learned so far. Okay. We also learned that we have two types of acids and bases. The first type of acids is basically called a strong acid. And the strong acid is the acid that dissociates fully, or the base that dissociates fully, if we're talking about strong base. So if you have a strong acid, which is HA, and you dissolve this in water, so this will dissolve fully to give H plus and A minus. So that means if you started with 0.5 molar of this one, after you dissolve in water, this will no longer exist in that form, and it will exist as 0.5 of this, moles of this, and 0.5 moles of that. Okay, now if you have, let's say, H2SO4, which is a strong acid. So H2SO4. So when this dissociates, it will give you basically 2 moles of hydrogen ions and 1 mole of the sulfate ion. So if you start with, let's say, 0.5 moles here, so here it will be 2 times 0.5, and here it will be 0.5. Okay, so always you have to take in consideration the coefficient here. So if you were to find out the concentration of this acid, then if this is number of moles, then the number of moles here will be times 2. And if this is the concentration will be times 2. Now, before we proceed, since I have mentioned these two different things, you always have to differentiate between two things. If you are given in solution in the question the number of moles, or if you're given the molarity. If you are given the molarity, that is the number of moles in volume. And generally, you're talking about number of moles, moles here, and the volume in decimeter cube, or liter, if you like. The number of moles is just number of moles. So generally, you will be given the number of moles and you'll be given the volume of your container. So if you are given the volume of the vessel or the container, then the number of moles, you'll divide them by the volume in order to get the concentration. Okay, so in this case here, if we were told that the number of moles of sulfuric acid is so and so, like 0.5, for example, so the number of moles of the hydrogen ion is 0.5 times 2. But let's say that everything was dissolved in 2 liters. So 2 times 0.5, these are the number of moles, divided by 2 liters. So 2 cancels out 2, so you have 0.5. And this 0.5, basically, you'll use it to do minus log the hydrogen. Fine. And if the amount here, it was 1 liter, so it will be 2 times 0.5 divided by 1, which is 1. And then you place it here. Okay. So this is basically the in relation to the strong acid or strong base, and that the strong acid and strong base, they dissociate fully. Okay. Let's just remove that. So far we've learned 4 formulas, and we learned that the strong acid and strong base, they dissociate fully. And if we have the concentration of acid or base, we can use that concentration directly into this equation. We can just plug the values of hydrogen and OH in here and find out pH. And if you are given the concentration of hydrogen or the OH, you can use the 10 to the power of minus the pH or BOH to find out the concentration of the hydroxyl or the hydrogen ion. Okay, next, basically, we have the weak acid and weak base. In relation to the weak acid and weak base, they dissociate partially, which means the following. So if you have HA, you dissolve it in water. As you can see here, I have created equilibrium. So it's not an arrow with one head, but 2 directions here. So basically here you'll have A minus and H3 plus, H3O plus. Fine. So for this one, if you started with, let's say, 1 molar of this, and you dissolve in water, only small portion of this will dissociate to give A minus, and the rest will remain the way it is. So let's say that 0.95 molar, it will stay the way it is, and only small amount will dissociate to give this and this. Okay, and that's why in this case we cannot use the initial concentration here of the acid given to plug it into the equation of pH equals to minus log the hydrogen. We can't use this directly. Why is that? Because, as I said, if we have 1 molar, so the 1 molar here is not, it will not all go and form 1 mole or 1 molar of this and 1 molar of that. Okay, only small portion of that of the 1 molar will be dissociating and giving a portion here and a portion here. Now, to do this, basically, we require a little bit of calculation. And that's why we do the ice table. But before the ice table, we need to write something called Ka for this reaction. And Ka is similar to, if you remember, the Kc from last year. So basically, it is the concentration of the reactant over the product. The product over the reactant. So here we have A, and here we have hydrogen ion divided by HA. Now, if Ka is big, that means the dissociation of Ka of this HA is big. If the value of Ka is big, that means this acid here is dissociating more. In other words, basically this acid is giving more hydrogen ion into the solution. But if this Ka is small, that means the acid is not giving enough hydrogen ion into the solution. The acid like to stay the way it is as HA. It doesn't like to dissociate. Okay, so if we look at this equation mathematically, if we have a big value of HA, that means the Ka, it will become low. And if we have a small value of HA, that means HA will be big. So it depends basically on the concentration of HA. If the concentration of HA after the solution became small, so the HA will be big. And if the concentration after the solution is big or still big, then the Ka value will go down. So, so looking at these equations here, you don't need to learn how the equations are driven, but it's just for your knowledge. So the Ka basically equals to the concentration of the products over the reactant. If you rearrange the equation and take the minus log, you will end at the last equation here, and that is BH equals to pKa plus the log of minus A over HA. Okay, so this equation is called Henderson equation, and it's really important. So this is the fifth relation that we need to learn today. So the first relation was this one. The second relation is this one. Third relation is this. Fourth is that. And the fifth is this equation. Fine. Okay. Now we came to know about strong acid, how to deal with it. Strong base is same thing. Weak acid, you don't directly apply the values into the equation, but rather you have to basically do a little bit of calculation in order to find out how much of the hydrogen ion has been dissociated. And then after that, you can take that amount of information and then plug it into the BH equal to minus log concentration of hydrogen. And therefore, basically, you require to understand that the weak acid requires basically a bit of information about its Ka value. Ka value is telling you how much of this acid dissociated. Is it so much or so little? Okay. So the first question here is a comparison between acids. And in this comparison, or comparison between bases as well. And in this comparison, basically, you are given Ka values and Kb in case of bases values, and you are asked to compare between these values, which acid is stronger. Now, if you are not given values in the lab and you want to compare between acids, and these acids, you were told that they are of the same concentration, let's say 2 molar of this and 2 molar of that. So there are ways to compare the concentration, or to compare the strength of acidity, and one of which is just basically to measure the pH. So if you were to measure pH of 2 molar hydrochloric acid and 2 molar of acetic acid, you will find the pH of the 2 molar of hydrochloric acid to be lower than the 2 molar of the acetic acid. And the reason is as follows. In case of HCl, if you have 2 molar of it, then the concentration of H plus is 2, and concentration of Cl minus, which is not important to us here, is 2 as well. So the pH equals to minus log 2. But in case of CH3COOH, when this dissociate, the 2 molar here you started with, it will not equate to the concentration of the hydrogen ion here. So here you'll get acetate ion, which is CH3COO minus and H plus. So here in this case, you cannot say that concentration of acetate ion is 2 and the hydrogen ion is 2. This is wrong and this is wrong, because as I said, the CH3COOH is a weak acid, and therefore basically it will not dissociate fully. It will only dissociate partially, and therefore this value, it will be far below 2, and this value will be far below 2. Maybe it's like 0.0 something, like 5 or something, and same applies here. So, and this basically requires a little bit of calculation in order to elucidate the concentration of hydrogen and the acetate, and we'll do this in the next couple of problems. Okay, so now you are just given the values, and you are asked to find out which acid is stronger. And in both cases, you should understand that these acids are weak acids, but here you are comparing weak acids, because the value of, if it is a strong acid, always the value of Ka is 1 or more than 1, or way beyond 1. So when there is Ka mentioned in a question, you should immediately understand that what they are talking about is a weak acid. They don't mention Ka for a strong acid. And if there is Kb in the question, you should automatically understand that what they're talking about is weak base, because strong bases, they don't have, or they don't mention their Kb value for the same reason. Okay, so here, if we want to look at these two acids, here we have a value of Ka, and here we have a value of Ka. This value of Ka is 2 to the times 10 to the power of -1, and here it's 1.8 times 10 to the power of -5. So obviously this value here is bigger than this value. That means there is more of hydrogen ion goes into the solution from this acid as compared to this one. This one is only small amount of this acid dissociate as compared to the other one. In case of bases, here we have Kb and Kb, and as you can see here also we have the value of 6.4 times 10 to the power of -4 for this base, and 1.8 times 10 to the power of -5 to this base. So obviously this value is bigger than this value, and therefore this base is stronger as compared to this one. Okay, now if we want to take the pKa, as we agreed in the class, is P means minus log. So if we have Ka, so pKa equals to minus log Ka. Okay, and as we said in the class, we normally use the pKa in order to change these difficult to compare numbers into like small numbers that we can compare them easily when we read them. So as you can see, pKa of this value, back again to the acids. So here the concentration or the Ka of this acid is 2 times 10 to the power of -1, if you take the pKa, it will be 0.7. And if you take the pKa of the other acid, it will be 4.74. So as you can notice here, there is inverse relationship between Ka and pKa. When it was Ka values, you always just look at the bigger value and you say it is associated with the stronger acid. When you are given pKa value, you look at the smaller value and you say it is associated to stronger acid. So you see the pKa here is 0.7 as compared to the other one, 4.74, whereas Ka of this one, of this acid, it was bigger than Ka of this one. So you should always be careful about this. In case of pKb, it's exactly the same concept. So in this case here, we said this number is bigger than this number. So basically it is a stronger base as compared to this one. But when we took the pKa value of this one was 3.19, and for this one it was 4.7. So this one, the smaller number, it indicates the stronger base, and the bigger number indicates the weaker base. So it's an inverse relationship between the two. Okay, so I hope you enjoyed the video so far. I'll stop here and then we will continue in the next part of this video, the rest of the problems mentioned in this tutorial. Thank you.